Well, good evening, and welcome to Kopernik Observatory. My name is Drew Desker. I'm the director here at Kopernik, and it's great to have you here. I also want to welcome those watching on the live stream. Yeah, I don't know what it is about this spring and the rain, but for some reason it seems to like Friday evenings. Although actually I did see some sun, so. Hold on, we may get lucky for doing some observing afterwards. Let's just see here. So there's definitely some familiar faces here, but it seems like there's some new faces. Anyone here for the first time? All right, very good. Anyone here who is members? All right, pretty much the other half. What I'd like to point out is that those people that raise their hand second have a sort of valuable piece of information. Kopernik Observatory and Science Center belongs to what's called the ASTC, Association of Science and Technology Centers, and it's a consortium of over 380 other science centers that honor each other's memberships. So if you like this kind of a place, a Kopernik membership is actually very reasonably priced, and you could go to the Franklin Institute down in Philly, you could go to the Intrepid down in New York City, you could go to the Robertson Museum in Binghamton. All for free with using that card. And I took my daughter down to the Franklin Institute a few years ago, and had the two of us just paid regular street price for an adult and a student, it would have been more than the cost of our yearly membership. So if you like this kind of place, you might want to consider getting a membership. So Kopernik just finished its 50th anniversary of being a public observatory and informal STEM education facility. And we do a number of things. This week we had a couple of school groups in doing some STEM engagement. We do a very extensive summer camp program, actually, on our website here. If you come down here, this will be the 33rd year that we've done STEM summer camps. For students as young as going into second grade up through high school, and again we got a range of topics. Not all of it's astronomy, but we certainly do cover that topic. Do some ecology. We do discovering the beauty of art, patterns through art. So that's sort of where that STEAM sort of comes in. We're doing some astrobiology. We're doing some immersive innovators, which is 3D, virtual reality and augmented reality, having students actually create their own virtual reality environments. We're doing some CAD and 3D minerals. I run a program called Return to the Edge of Space, where our students will build a payload that will send up on a weather balloon. That weather balloon will reach over 100,000 feet. We fly GoPro cameras on it. We also fly some ham radio slow scan television. This year we're actually going to fly a Geiger counter, and we're going to try to look at what kind of cosmic ray increases we see as we go through various altitudes. So we're looking forward to that. So if you have a child or grandchild that might be so inclined, definitely want to check out our summer camps. And let me go back here one. And the other thing we have coming up here is actually our Rocket Fest. This is I think our 16th year that we do this, where families will register. They'll come up here. Actually, some have come up here tonight to pick up their rocket kit. They'll build it over the next couple of weeks. And on June 7th, we will have over 125 rockets that we will launch over about a 7-hour period. So you'll sign up for a certain launch window. We'll come out. We'll have you. We'll check out your rocket, make sure that it's ready to go. We'll put the engine in. Then you walk out, and you get to hit the button that sends it skyward. And these rockets, depending on what kind of engine you put in, go anywhere between 500 and 1,000 feet. And we get a large percentage of them back. But one of the things I really like doing are these Friday night programs. From March to mid-December, every Friday night we do some sort of presentation on some aspect of science and technology, not always about astronomy. Tonight's program is evidence of that. And it's really an opportunity for us to sort of continue our learning, especially for those youth that are here in the room. Your schooling doesn't end, your learning doesn't end at 12th grade or in college. It's a lifelong pursuit. And I think you can sort of see with some of the gray hair in here, there are people that do espouse to that. And I personally, I wish I could live another, 50 or 100 years. I remember watching Neil Armstrong walk on the moon. And I'm wondering, how will technology, progress over the next 50 years? I mean, when I was your age, Anthony, I used to have to walk to the TV to change the channel. Now, of course, you can watch it on your dad's phone. But what's going to happen with medicine? Software. What these events are, or what these evenings are really about, is just making you aware of what's out there, and hopefully, especially for our youth here, inspiring you to think about maybe what your career might become. So we've been doing these Friday night programs since before even I got here in 2011, and in 2020 we had to stop meeting because of COVID. We couldn't put a bunch of people in a room at the time. So I said, okay, fine, we'll hold off on doing these things for a couple of weeks until this COVID thing blows over, and didn't exactly play out the way we'd hoped. So about a month or so later, we decided, look, we've got all these speakers lined up. Why not get them to zoom into here? We'll just turn it back around and put it out on our YouTube channel. And we've been doing that ever since. And even though now we are able to gather back again, we still continue to do this. And we now have over nearly 14,000 subscribers on our YouTube channel from people literally around the world. In fact, I believe Lindsay is watching this evening. Actually, for her, it's tomorrow morning. She's finished breakfast and is putting away the dishes right now. So you all want to say hello to Lindsay?
Hi, Lindsay.
All right, there we go. All right. So what's also great about all of these programs is that they're on our YouTube channel, and they will continue to be there. So last week we had a talk about the Galapagos Islands. The week before that we had a Southern Tier Robotics program. We actually had two week-to-week, back-to-back weeks on robotics. We've had talks about AI, the Fermi paradox. So you definitely want to check out our YouTube channel. But those are just our Friday night programs. Part of why we've gotten such a large number of people that have subscribed to our channel is that, we're just about there, 13.9K subscribers. We do a number of observing sessions. So we've done meteor showers, we've done eclipses. In fact, a couple of weeks ago, a couple of months ago at this point, there was a lunar eclipse that started at 2 in the morning, and Jenny Cardy, who's driving our live stream, as our live stream astronomer, came up and basically did a live stream for the entire 5 hours of that lunar eclipse, and we had perfectly clear skies here. And Jenny put a really neat. Unfortunately, are we going to get? Yeah, no, we won't. Here we go. She put together a really nice time lapse of the eclipse that happened back in March. And for those of you who are into astronomy a little bit, this was actually done with a telescope called a C-Star, which is an extraordinary device that is really very inexpensive and does some great work. So we're now finally into totality. We have that blood moon where the light being refracted through the Earth's atmosphere is predominantly the low frequency red. And then finally, coming out of eclipse. And then Jenny changed the exposure so that we can start seeing the details of the moon again. Is that Kopernik crater near the bottom? Tycho, I say. So anyway, definitely want to check out our our YouTube channel, either live or at your convenience. As I said, these Friday nights are really an opportunity for us to learn about the world, about the universe, and I'm very happy to be able to bring Dr. Nathanial Frissell, who teaches physics down at the University of Scranton, and shares one of my favorite hobbies is ham radio, and so that will feature prominently through his presentation. And so, Dr. Frissell, if you want to come up, and we'll get your presentation up here. And let's start from the beginning.
I've got my own. Hello. Hi, everyone. How are you? It's really nice to meet you and to be here this evening. And hi to Lindsay as well, who's on the live stream far away. So yes, I'm Nathanial Frissell. I'm a associate professor of physics and engineering at the University of Scranton, and I'm a ham radio operator. And most of the time, I start with the question, how many people in the room are ham radio operators? And but today I might ask, how many people are not ham radio operators? I've got a couple. Okay, a few. All right, that's good. So I've got lots of tutorial information to explain what we're doing. So, and why ham radio is important to this space weather that we can do together. So, first of all, what is amateur radio? It's a hobby. It's a licensed radio service for people who are communicators, builders, and experimenters, people who want to learn about how radio works. It's a wide-reaching demographic. We have come from all ages and walks of life. We have some very young ham radio operators. We have some very experienced ham radio operators. And one of the key things that makes ham radio operators special is we're licensed by the federal government. You have to take a basic licensing knowledge exam where you learn some basic electrical engineering, basic science, and then you get a call sign. And so that call sign is what identifies you in the air. My call sign is W2NAF. And so you'll see these call signs throughout the presentation. And ham radio, you will see, is actually a way you can actually use ham radio signals to remotely sense what's going on in space and the upper atmosphere. And so I got my ham radio license when I was in high school, and it eventually caused me to go pursue a PhD in electrical engineering at Virginia Tech. And while I was pursuing this PhD, studying the ionosphere, I came up with this organization called HamSCI, the Ham Radio Scientists in Investigation. And so this group is a community of both professional space scientists, so people who are actually professors at universities and research scientists across the world, and volunteers who are ham radio operators, or maybe they're retired engineers. We all come together to do science together. So how does this all work? Well, the main thing that I'm interested in, and our group is interested in, is something called the ionosphere. The ionosphere is a region of the Earth's upper atmosphere that's electrically charged. And the reason it's electrically charged is because the ultraviolet energy from the sun will ionize the neutral particles in the upper atmosphere from about 80 kilometers altitude up to about 300 kilometers altitude. So that ultraviolet energy will knock electrons off of atoms and molecules, and you'll get free-floating electrons, free-floating positive ions. It'll create a gas called a plasma. And this plasma can cause radio waves to bend back down to Earth and changes what direction the radio waves go. So the ionosphere is generated by the solar ultraviolet energy. So during the day, the ionosphere is stronger, and it's actually more structured. So you have the D region closest to Earth, then the E region, and then the F1 and the F2 region up at 200 and 300 kilometers altitude. At night, the free electrons, this photoionization stops. The free electrons can find the positive ions, and they can recombine, and the ionosphere becomes less dense. It doesn't go away completely. You still do have an E layer and an F region at night. So, and then when the sun comes back, the ionosphere gets stronger again. So how does this affect radio signals? So if you choose the correct radio frequency, which is generally between like 3 to 30 megahertz, those radio signals can be refracted back to Earth, and it lets you talk far away. So here, my friend Tamitha, who's in California, is trying to talk to me over in Pennsylvania near Scranton, and whenever you see a red line, that means that we're able to communicate with each other. This is what we call a ray trace diagram. So the colors here represent plasma frequency, which is related to electron density. And you can see at night the electron density is lower, so there's less refraction. The rays escape into space. And if I zoom ahead a little bit, we'll get dawn coming. You see how the ionosphere builds up, and the radio waves bend more, and you can get this multi-hop propagation. So that's ionospheric skip propagation. Now this is for 14 megahertz. It turns out that the frequency that you use very much dictates how much bending occurs. So generally, if you are using a higher frequency, you're going to have less refraction or less bending. So here's a ray trace diagram for 15 megahertz. You can see that one hop will get you 1,500 kilometers. If you were to use the same ionosphere and go down to 10 megahertz, to get that same 1,500 kilometers, you may have to use 2 hops. Okay? So, and that's why throughout this presentation you may see us referring to different frequencies, because we can basically see different parts of the ionosphere looking at these different frequencies. What do you think happens if we go too high in frequency? It goes straight through, yeah. So if you go too high in frequency, usually above 30 megahertz, it'll escape out into space and you can't talk to anyone. What happens if you go too low in frequency? And the ionosphere is strong. You might not get distance, or during the day, there's a D region ionosphere, it can actually absorb those lower frequencies. So there's kind of a sweet spot of frequency that you want to be in order to make this work. So I'm from Scranton, and this is my house near Scranton, and I wanted to say, this is something that, you can do at your own house. So here's my house. You get to see my ham radio station. This is the antenna I have. It's a very simple wire antenna. It's about a little longer than 100 feet long, and maybe it's just hung up in trees about 40 feet in the air. And then here's my ham radio station. I actually upgraded it recently, so I have a fancier radio here now. But but it's pretty similar to what it looks like today. Here is a COVID era recording I made of me listening to a station on that antenna, and you can hear, this is on 14 megahertz again. You can hear what some of these ham radio contacts sound like. See if you can understand what they're saying.
Thank you from Lima Yankee number 3, number 1 Alpha.
Feel that atmospheric noise.
QSO station from New York. Whiskey Echo 2 Charlie Alpha Tango 59 Fiendelis John. January, October, November. Good morning.
So that's what a typical single sideband contact sounds like. And you might have heard, he said at the beginning, thank you. This is Lima Yankee number 3, number 1 Alpha. That is his call sign. And so you can look up on a website called qrz.com. You can type in someone's call sign. You can find all sorts of interesting information about them. People like to post biographies and pictures and fun things like that. So I was able to hear this station from Lithuania, 4,200 miles away from my house in Scranton. And so that's one of the ways ham radio operators normally communicate. Now, you know what the best part about ham radio is? It doesn't always work. Now you might be like, now that's a really funny thing to say. But if you had something that you picked up every day and it always worked, you'd be like, okay, that's kind of routine. But the thing is, with ham radio, there's so many different frequencies, so many different things that are going on that are all affected by space weather that sometimes you're able to talk to Australia, sometimes you're not. Sometimes you're able to talk to England, sometimes you're not. You may be able to sit here in New York, and you might be able to talk to California, but maybe you can't talk to New Jersey, which is right next to you. So, and it's all of trying to understand how the system works and knowing what frequency to use when and why it sometimes works and why it doesn't. That is a really fascinating thing about ham radio. It's so fascinating that you'll see that there are thousands of people around the world that actually create contests around figuring out who can understand the system the best. So we live, this is not drawn to scale. This is a NASA image. Okay. To be careful, you know, I'm speaking at Astronomy Observatory. We have to talk about, you know, scale sizes and things like that. Not drawn to scale, but this is the geospace system. So we have the sun, we have the Earth over here. The sun sends out a solar wind that carries, that's a plasma that carries with it an interplanetary magnetic field that blows against the Earth's magnetosphere, which is over here, and that magnetosphere threads the ionosphere that I was just talking about. And so you can have all sorts of things that happen here. Like if you have a solar flare, that can suddenly ionize the ionosphere. If you have something called a geomagnetic storm, that can cause a massive reconfiguration of the magnetosphere and affect the ionosphere as well. All of that space weather affects how the ham radio signals work. And so here's a good example of that. Here's what we call an X-class solar flare that took place in 2017 as observed by the NASA Solar Dynamics Observatory. And the thing about solar flares is that they put out not only UV energy but also X-ray energy. And that will get, and it will ionize the lowest levels of the ionosphere called the D region. Now the D region ionosphere is actually not helpful to ham radio because we call it the darn D region. It actually absorbs radio signals rather than helps refract them. And the reason for that is that atmospheric densities are higher there. So an electron, when it pulls in some radio energy, it's more likely to hit some other particle and damp the signal before it has a chance to re-radiate. So it's what we call collisional damping. So when that solar flare takes place, you should know that these ham radio signals, certain types of ham radio signals, digital ones and Morse code, there's a big Morse code contest this weekend. We have automated receiving systems all over the world that are constantly listening to these digital and Morse code ham radio signals, and they're keeping track of who's talking to who and who's hearing who. And you can go and you can download all that data and you can see what happens. And so for that particular solar flare, I was able to download the data from those websites, and I saw in the 15 minutes before the solar flare, I observed 13,245 communication paths from the ham radio system on these different frequencies. In the 15 minutes after that solar flare, it went down to just 2,500. So you can really see in the ham radio data the effects of this space weather. And so here I'm able to take the data from these websites and use ham radio not simply as a communications tool, but actually as a tool for remote sensing and science. And that's how I've built up HamSCI, and that's how I do the citizen science that I do today. And here's another way of looking at that exact same solar flare. So this is, here's the solar flare, the solar flux, X-ray flux measured by the GOES spacecraft. So you can see one solar flare took place here. There's another solar flare. This is the ham radio communications over Europe. This is distance from 0 to 3,000 kilometers between transmitter and receiver as a function of time. You can just see how this one just knocked that out, and then the second solar flare knocked out the communications there. And this was on 7 megahertz. So that's in Europe. Down here is the United States. Now, at the same time, you can see that the solar flare knocked out Europe, but not the United States. Why? Yes?
Located differently?
It is located differently. Differently relative how?
Sun.
To the sun, yeah. So this dotted curve right here shows you the solar zenith angle. And you can see when this is highest on the plot, that's noon. So throughout this entire period, Europe was on the day side exposed to the sun. The United States was still in dawn at this time, or in the night side, so it was essentially shielded from the solar flare. So yeah, so we're using all this to actually do science. So, quiz question. What well-publicized astronomical events took place over North America on October, that should say 14th, so it should say October 14th, 2023, and April 8th, 2024. Yeah, eclipses, that's right. Oh, look who, hey, Anthony, who's that? That's you, yeah. Yeah, so there were solar eclipses, and so this was taken in Scranton where there really wasn't much to see because of the clouds. But on the radio, we got great observations, and then this was taken by one of our volunteers, Michael Howen, AC0G. He got a beautiful photo of the eclipse. And so eclipses actually are also affect the ham radio signals because they're kind of like temporary nighttime. So HamSCI, we created this Festivals of Eclipse Ionospheric Science, where we created many different experiments to have ham radio study the effects of the eclipse on the ionosphere. Now here's this is actually a model of the ionospheric electron density changes caused by the eclipse. So you're used to seeing eclipse movies where it shows a shadow of the moon on the Earth. This is not the moon shadow. This is actually a physics-based model calculating the total electron content, differential total electron content of the ionosphere and how it's changed based on the total solar eclipse. So you can see how this might affect the ham radio signals. And here's another ray trace diagram. This is there was also an eclipse back in 2017 that we did something similar for, and you can see it's not day and night that's causing these changes here. That's the eclipse passing through. So we ran many different experiments. I'm going to show you, we ran like 5 major experiments. I'm going to show you results from 3 of those experiments tonight: the Solar Eclipse QSO Party, the Personal Space Weather Station, and the medium wave AM Doppler experiment. Some other very cool experiments as well. I do want to tell you a little bit about the University of Scranton, and the reason I'm putting this here is because we just installed a new ham radio station a little over a year and a half ago there, and we got to use it for the solar eclipse. So the University of Scranton, we are a Jesuit liberal arts university located in downtown Scranton. We have undergraduate electrical degrees in electrical, computer, and mechanical engineering, and physics, and more. So if you're interested in any of those, we'd love to have you check us out. And this is the outside of the Loyola Science Center, and it is marked with all of our ham radio antennas. So our club station is right here. We have from the Binghamton Amateur Radio Group that got to go visit. Is this not the best view of downtown? Absolutely gorgeous, gorgeous view. And then here's our 2-meter 440 megahertz satellite antennas over here. We have our vertical antennas for 6.2, 440, 1.2 gigahertz. We have our fan dipole for 40 and 80. We have our 40-foot antenna tower with the DX Engineering Skyhawk for 10, 15, and 20 megahertz. We have a repeater too. Absolutely beautiful facility, and you can hear a little bit about that and the eclipse.
Students in Lackawanna County are learning more about radio waves and their connection to the atmosphere and to space.
It's part of a large research project at the University of Scranton. Newswatch 16's Emily Kress tells us more about how the eclipse can change how those waves work.
It's an all-day affair at the University of Scranton preparing for the total solar eclipse. While some students are just watching, others are working hard on research.
That's a lot of velocity change.
We're looking to see how this particular eclipse affects the ionosphere and the upper atmosphere. Every single eclipse is a little bit different, going through a different path.
Dr. Nathanial Frissell is an associate professor of physics and engineering at the university. He says this research has been years in the making. Last fall, the university installed this tower to get a student ham radio station up and running at the Loyola Science Center. Students and other community members are able to connect with people across the country and the world.
When the eclipse comes through, it cuts off the sun and that photoionization, and so now the radio waves aren't bent the same way. And so when you receive the signals on the other end, or you don't receive the signals on the other end, if you look at things correctly, that can be attributed back to the eclipse.
Research like this is important because if we can understand how radio propagation works, we'd be better suited in cases like an emergency where, processes such as, phone lines or any other electronic communication wouldn't really work.
Students spent all day in the ham radio station since other parts of the world experienced the eclipse long before the eclipse reaches our area. The university was one of 5 chosen as part of a citizen science project with NASA. Through this research, students are helping to document history.
It's a pretty cool experience. It's like the environment and how everything is, all the people around here. It's very interesting to see all play out.
That feels pretty great, knowing that we're at the front of this, and would not have expected to have this great opportunity when I first came to the university.
Students will now spend their time breaking down all of the data collected. Emily Kress, Newswatch 16, Scranton.
So I can show you some of the results. So first experiment we did was something called the Solar Eclipse QSO Party. I told you about those radio contests where people try to make as many contacts as they can within some period of time for points. Well, we turned that into a scientific experiment. We created our own radio contest where we had hams communicate before, during, and after the solar eclipse, and then we used those data sources that I listed before. We awarded certificates to people who got the highest points, and then we were able to generate plots from these data sources. And so this is a summary plot from the April 8th eclipse, and we're looking at 24 hours worth of data here. We're looking over the continental United States, and we're looking at 6 different frequencies: 1.8 megahertz, 3.5, 7, 14, 21, and 28 megahertz. And you can see what we call the diurnal variations. So that at nighttime, the upper bands don't work so well because the ionosphere is weaker and the signals escape into space. The lower bands are good. Then here's the daytime where things flip. The lower bands get absorbed, so most of those communications go away, but the upper bands work because the ionosphere is stronger. During the eclipse, what do you see? You actually see those low bands start to open up and work again because of the temporary night-like conditions from the eclipse. We have a few postdocs working for the HamSCI project. One of them is at the New Jersey Institute of Technology, Dr. Kuldeep Pandey. So he's been doing a deeper dive into this data, and so here you can see his plot of 7 megahertz over the continental United States and 7 megahertz globally. And you can see here that this is hours before and after maximum eclipse. So again, you really see a nice increase in the 7 megahertz band there. This means that this distance on the side here is how far away of a radio station you can talk to. So if it says 4,000 here, that means you, at this particular time, you could talk to a radio station 4,000 kilometers away from you on that particular frequency. So you can see how that changes. And then that's just over the continental United States. This is globally. So you can see here the same effect, but you also see this is what we call that second hop propagation, and you can see that also opens up during the eclipse. Here's on 21 megahertz. So you can see the effect is a little bit different over the continental United States. It's actually rather difficult to see the effect of the eclipse this time. And on the 21 megahertz globally, the second hop is affected. Now, one thing I have to tell you, we did this experiment back in 2017 as well, and I did the analysis that time. That was at a low point in the solar cycle. So the solar cycle is every 11 years, and when the solar cycle is at its maximum, which we are right now, or we're just getting past maximum, the ionosphere is stronger and there are more sunspots. During the 2017 eclipse, it was at the low point in this sunspot cycle. This was very obvious during the eclipse that the 21 megahertz band just shut down. So there are definite differences that we could also see in terms of solar cycle, which is really cool. My postdoc also looked at continually operated transmit receivers. So he picked out just those stations that the transmitter and receiver maintained contact for the entire 8-hour period. And the thing that was most interesting on this one is if you look at this one, this is April 8th. This is the day of the eclipse. That's this column here. This is April 9th, the day after the eclipse. So this is like your control day. So on the April 8th day, you can actually see what looks like an eclipse effect on 21 megahertz. But you see this green dashed line there? That's the eclipse. So this effect is actually happening after the eclipse. If you look at the next day, that feature is not there. So you're like, well, that's funny. Why is that delayed? And what Kuldeep figured out is it's likely because this eclipse actually transitioned and merged with the dusk sector. So that actually kind of extended the effect of the eclipse in a way that wouldn't normally have happened. So that was a really neat result from that. Now, that's all data analysis that I've showed you here. So that's actual data. We're also doing modeling of it. So we have a collaborator, Dr. Joseph Huba, that runs this physics-based model called STAMI-3 of the eclipse. And he gives us those electron density outputs. And then Kuldeep puts it through the ray tracer. And then he has a grid of transmitters and receivers in the US and over in Europe that he simulates the data. So, whoops. So over here, this is 7 megahertz. On all the way to the left, this is actual data. And then over to the right, this is a model. And where it's below 125 kilometers, we're modeling E-region refraction. And on where it's above 125 kilometers altitude, we're modeling F-region refraction. We're actually able to do this ray trace modeling to take the data and compare it with a physics-based model and see how well we understand things. And you can see we really do have quite good agreement. Well, here, if you look at 7 megahertz, you can say, okay, this feature looks more like this one, not like that one. So we can say that this 7 megahertz data was probably refracted off of the F region, not the E region. And so you can do that by doing this sort of data model comparison. And we're doing the same sort of thing for 21 megahertz. The model actually only gave us F region refraction for there. So here are his preliminary results on this. So he's working on putting this into a manuscript for future publication. So that's one experiment. Another experiment we did is something called the Personal Space Weather Station. And we're actually trying to get people across the world to put these receivers out. And I'll talk a little bit more about putting these receivers out later in the presentation. But we've got these different receivers. We call them grape receivers. These are grape 1 and 2. And then this is called the Whisper Demon Grape. And we can have a whole discussion after about why they're called these things. But that's what they're called. And the main objective of these grape receivers is not to measure signal strength or just if you had the communication or not, but rather you're measuring a Doppler shift. So here there is a radio transmitter in Colorado called WWV, and it's been running for over 100 years, and it's run by the National Institute of Standards and Technology, and it transmits very stable atomic clock accuracy frequency on 2.5, 5, 10, 15, 20 megahertz, and sometimes 25 megahertz all day long. And if you send that radio signal up and then back down, the ionosphere, as the ionosphere moves, it will actually make this path longer or shorter, and that will cause the observed received frequency to change a little bit, and that's the Doppler shift. Now, it used to be when WWV was first put on the air, and for many years after that, there was nothing better than that you could get than the received frequency of WWV. That was your standard. Today, we have these things called GPS-disciplined oscillators, where you're using the GPS signal not to tell you where you are, but to tell you what frequency you're on. And so you can use that GPS disciplined oscillator as a $100 laboratory grade frequency reference at your home station, and you can now measure very tiny Doppler shifts on this. And so we did this during the eclipse here. And so WWV is in Colorado. There's actually another one, WWVH in Hawaii. And then there's CHU in Canada. Here's my station. We had receivers all across the country, but I'll just show you some results from my station. This is one from the October 14th annular eclipse. And what you're looking at here is listening to 10 megahertz, the station in Colorado. And then this is Doppler shift. Zero, if it's zero, that's right at 10 megahertz. This is all at the top is plus 5 hertz. All down at the bottom is minus 5 hertz. And then this is 24 hours worth of time. So throughout the night, you get all sorts of oscillations like traveling ionospheric disturbances and things like that. Then look at this big feature. That's dawn. So when the sun comes up, the ionosphere builds up, those path lengths get shorter. That gives you a positive Doppler shift. Then the eclipse comes on. The ionosphere starts to recombine. The path lengths get a little longer. That makes a negative Doppler shift. So this is the negative Doppler shift of the eclipse. And then the eclipse ends. It's like dawn again, positive Doppler shift, and then things stabilize. And so that's from the, we had beautifully cloudy skies. It was pouring rain at my house during this eclipse, but we were all watching this chart be made in real time, and that made it worthwhile. So, and then here is observations from my house from the total solar eclipse, and now we have the newer system that we have can do 9 frequencies at a time, actually more than that, but we were monitoring 9 frequencies. So here's 20 megahertz, 15 megahertz, 10 megahertz. That's like a beautiful eclipse signature right there. And then at 5 megahertz, where it's mostly being absorbed during the day, you get a little tiny wisp of a signature there. And then we also have great observations from CHU, which is a Canadian station, in Ottawa as well. So these are just a few of the many beautiful observations we got from that eclipse. Another thing, how many people here have ever listened to AM radio in your car? Okay, so even the non-ham radio operators have probably done that, right? Did you know that those AM radio signals are also affected by the day-night variations? Yes? So, okay, right? So at night, you can hear stations that are farther away than you can during the day. Well, you can get the same effect by during the solar eclipse. So one of our volunteers, Nick Hall Patch, organized people to listen to AM radio throughout the whole eclipse and record all of that information. And he got a great data set of listening to AM radio for both of these eclipses. And here's just one example of signal strengths of AM broadcasters heard in Arkansas, from Texas and Ohio in the daytime. And so on the left here, this is April 7th, 2024, no eclipse. You can't hear these stations at all. And then look at what happened during the eclipse day. The signal strengths just came right up. And so beautiful observations. So you can make these sorts of observations yourself at home, and we don't have any eclipses left, but guess what? Space weather happens all of the time. So every morning and night you get that day-night transition. We still get solar flares, we get geomagnetic storms, we get all sorts of interesting features that we want to monitor. Plus you want to be able to monitor, you might be interested in shortwave listening yourself. If you go to HamSCI.org /WhisperDemon, or if you click around our website, you'll eventually come to this page, and it actually gives you the instructions for how you can build one of these things, one of these receivers. And the total cost is probably about $500 to $700 by the time you include the antenna and everything. You need this little thing is the radio. It's an RX 888. You can get them on Amazon. They do come from China. Then this is a Leo Bodner GPS disciplined oscillator. That's from the UK. So that's about $150. And then this is just a fairly modest Linux computer. Actually, this is a Ryzen 5. We're now using Ryzen 7 systems. But if you get like a B-Link computer, you can get those fairly inexpensively. And what's amazing about this system is you can listen to the entire HF band. Actually, you can listen with a better computer. You can listen from essentially a half a megahertz up to 60 megahertz, all simultaneously. And there's a new software-defined radio program called KA9Q Radio, which allows you to basically create as many slice receivers as you want of arbitrary size at a very computationally inexpensive way. So this computer can just handle all of it. And that's what's really driving our new systems. I do have to give you a little bit of a warning. This is a bit of an experimental system, so the instructions are changing and the codes are changing. So if you do go try and build this, you'll likely need some hand-holding. So you can contact us and we can help you get it on the air. It helps to have some good Linux skills, and so just know it's not totally plug and play. It's not like you go buy something at Best Buy and it just works out of the box. This is definitely for an experimentalist, but it works. And if you're a ham radio operator, this is great fun. This is the spectrum taken. That system, in addition to making the measurements, you can actually use it as a software-defined radio receiver that you listen to, like regular shortwave radio. And so this is a web-based interface of one of my friends, AC0G, the same guy who took the eclipse photo before, of the spectrum at his house, 30 megahertz of spectrum. And then here's what my ham radio station looks like today. Right, Anthony? Is this what it looks like? Yeah. Yeah, okay. So I'm what's that? Only the mouse is on that brown table? No, the mess? There's no mess. Well, you're not supposed to tell them about the mess. So down here I have my RX888s and my V-Links down here, and I'm actually running like 3 different experimental antennas. So you don't need all this equipment, but one of these will get you on the air. And then so here I've got 3 side by side, and I have a VLF receiver here, and I've got a network switch. So I'm really trying things out and working with stuff. I actually have a team that also helps me put these things in. This is Rob Robinette that many of you got to meet a couple weeks ago, and my students working on installing some antennas in my field that we're working with. But this is a screenshot I took of Whisper.live this morning, where you could see that system was receiving all over the United States and Europe, and even down in Neumayer Station in Antarctica. So we got the Whisper sound from down there as well. So beautiful, beautiful plot. And yeah, so you can actually set one of those up. Now the other part about participating in doing this citizen science is we're having a meteor scatter QSO party. Okay, did you know that you can reflect radio signals off of the ionized trails of meteors? Yeah, you can. So, yes. So it says, work the rocks, decode the pings, contribute to science as we strive to uncover the secrets of meteor scatter propagation. Join hundreds of operators on 6 and 10 meters, MSK 144, during the Perseids, and it should say Geminids, meteor showers. Transmit and monitor stations needed. So the Perseids are going to be August 11th and 12th, and the Geminids will be December 12th and 13th. And so we need ham radio operators to transmit and try and talk to other ham radio operators on meteor scatter, and also receive. And so even if you don't have a ham radio license, you can put up one of these systems and you can potentially collect data. So what is meteor scatter? As meteors enter our atmosphere, they leave trails of ionization behind them. And so we can scatter certain radio frequencies off of the ionized meteor trails. Today, this type of communication is extremely accessible to hams thanks to a special type of software called WSJT software and the MFSK 144 mode. We're going to demonstrate WSJT at the end of the presentation tonight. And so thanks to a recent law change, we can now operate MFSK 144 meteor scatter on 10 meters 28 megahertz and on 60 meters. We could do it on 60 meters before, but now we can do it on 10 as well. And Dr. Rob Suggs from NASA, he's also a HamSCI collaborator. He sent me an email saying that the theory says that the scattering process favors more meteors scatter in 10 meters, but there's another process called initial trail radius effect, which says that ionization trails of certain sizes can cause destructive interference of the signal, so that the trail radius is larger when the meteor ablates at higher altitudes, which happens from faster meteors. And so the Perseids have a geocentric velocity of 60 kilometers per second. The Geminids are 36 kilometers per second, which changes their average ablation heights and initial trail radii significantly. And so I'm actually fairly new to meteor scatter, so I'm still learning about this myself. But Rob is particularly interested in, are we going to get more scatter when we look at these? Are we going to get more signals on 10 meters or more signals on 6 meters? And that will help us to understand some of these meteor scatter and meteor ionization processes better. So if you would like to participate in this, visit hamsci.org/MSQP to get started. And we have nice instructions. We have sample plots of what the software looks like, the signals, the software over here. And of course, if you're not a ham radio operator, this is all probably very confusing to you, and you probably have no idea what to actually do. And it turns out that if you are sitting in this room tonight, you are in luck, because this room is filled with members of the Binghamton Amateur Radio Association, which meets here in this building on the third Wednesday of every month at 7 p.m. And so, if you would like to learn how to do more of this, I'm sure the Binghamton Amateur Radio Association members would be more than happy to help you get going with this. Is that right? True that. Wonderful. And the other thing you can do is you can also join the HamSCI project. You can click the blue button there. We have a Google group. We have over 1,300 members, subscribers, so we're not quite up to the 14,000 people on this live stream right now, but we do have over 1,300 members on our Google group. And we also have multiple Zoom telecons where you can work with us interactively and be a part of the science and the planning as well. So you can join that. And so with that, I'd like to thank you for coming. I'd also like to thank our sponsors, the National Science Foundation, NASA, ARDC, all of my collaborators, and the amateur radio community, and you. And after this presentation, we do have set up here a Yaesu FT710 transceiver that is connected to an antenna on the building, and they have it set up with the WSJT software. And we're not operating meteor scatter tonight, but we're operating another mode that's sort of related. It's called FT8, and it's used on the HF bands, and it works almost all the time. So even if you're not doing meteor scatter, but the interface is very similar. So if you want to actually try and see how this works, we'll be operating some FT8 afterward. So thank you very much.
All right, well, thank you. Before we go into the demo portion, are there any questions? All right, well, you clearly have, whatever questions they had, you answered for sure.
I hope that's the case.
No, absolutely. And I mean, this is, for many of us is new area. Yeah. But I think what's also neat about it is that who knew that you could bounce signals off of meteors? Well, some of us knew that, but just why all of a sudden can you at night now you're going to go out and tune on your AM radio and you're going to hear stations from Chicago and in Miami or Boston. I see people nodding their head. Yep, we're going to head right out and do that. And why does that happen? And so now you have at least a little sense of that. And this digital mode that we'll be demonstrating, this FT8, is become very, very popular. And what's particularly great, and I'm also a ham radio operator, is that when a band seems quote unquote dead, then you just don't hear any other signals on. But then you go down to these frequencies that the FT8 operators are operating on. All of a sudden, you start hearing all these connections, and then for very, very little power, you can literally go thousands of miles. And
this is a tremendous source of our data too. So just by operating this, you're actually contributing to the citizen science.
so
Yep.
all right, I walked away from my phone. Jenny, is there any questions off the live stream? Although you did do a poll of the people who are watching or participating. How many of them are ham radio operators, and how did that turn out?
Those that are, it's 60% versus 40%.
60 to 40% ham operators. So you are somewhat preaching to the choir, but maybe maybe we get some new members. Yes, you have a question? Yeah, hold on. Let me bring the mic over here.
So this is all new to me, but I was wondering, is your ham, when you broadcast your signals, is that a directional signal, or does it like 360 degrees?
It depends on the type of antenna you use. So every ham operator will have to choose an antenna, and that will be based upon their what resources they have in terms of land and space and budget and yes, budget, and also what their goals are. So you can create antennas that are omnidirectional, that do go all 360 degrees. You can also have antennas that do have a direction and will point in a given way.
Okay. And then the other question I was wondering is, how do you actually map it geographically? Like, how do you know that it's going to bounce off of the meteor shower trails or it's not?
That's a good question. So if you do have a directional antenna, you can try and point it towards the meteor trails. You will not be, you're going to be getting signals back. If you're operating at 6 meters and 10 meters, you're probably only going to be getting signals back from meteors because the ionosphere will not be strong enough at that time to support communications otherwise. And then the other thing you can do is if you look at the spectrograms and you actually look very carefully at the signals that you receive, there are certain signatures that you can look for that would help to support to say, yes, this was actually sent off of, refracted off of a meteor trail and not off of some other mode.
The meteor showers would be visible, optically at night. What about during the daytime?
If you have trails during the daytime, you could still operate off of them, even if they're not visible.
Yeah, basically, we can only see them at night, but meteors are coming. Literally, tons of meteors are coming in to our atmosphere every day, and the thing about meteor scatter is that, again, much like you can see that when you see a meteor, streaking across the sky, you only see it for a couple of seconds, at most, and so. Although the ionization trail may last a little bit longer, these are typically very, very short bursts of communication. But it is, in fact, you're able to bounce that signal off of that trail, and as I said, there are literally people that do this practically every day. Actually, I believe that even the military does some work with this as well. So.
I may not phrase the question properly, but what direction does the signal refract back?
I think, so I should preface this by saying that I am still fairly new to meteor scatter. Let me just say how this came up. The Solar Eclipse QSO Party ended. We were analyzing all that data, and about 2 or 3 months ago, they said, what do we do next? And one of our volunteers, who's actually, her name's Mackenzie Denton, KO4GLN, she's a student down at Old Dominion University. She said, why don't we do a meteor scatter QSO party? So everything I'm learning about meteor scatter is mostly from the past couple of months. But my understanding right now is that it would probably, if the meteors are coming in this way and you're sending the signal up this way, it'd probably backscatter back toward you, or maybe down a little bit too. Yeah.
So that'll be something we learn also as we do it.
Yeah. Yes, Bill?
When you're dealing with meteor scatter, the two stations pretty much have to be able to see the meteor, at least electronically or radio-wise, at the same time. The distance is based on how far away it is. You're bouncing off of it, it's bouncing back down. It does refract a bit, but it may be 400 miles, it may be 1,800 miles. And the other thing is when you're listening for meteor, if you listen to the the white noise from your receiver enough, especially when there's meteors all of the time, you'll hear these little pings, which is why we call it pinging. You'll hear these little pings. When you hear those, there are meteors out there that you can bounce off, or meteorites out there that you can bounce off of virtually any time. Now, a burn may only be a fraction of a second. A really good one may be 3 to 5 seconds, but most of them are fractions of a second, which is why this software is so useful, because it can very rapidly. Right, back when I started messing around with meteors, it was strictly Morse code, strictly CW, rarely sideband. Sideband was better, but you really couldn't understand anything because the signal comes back garbled because it's moving. Your reflection is moving at the same time that it's coming back. A lot of Doppler and a lot of noise on it.
All right. So just for those that are new to ham radio, I'm going to actually just turn the audio up a little bit so you can hear what this FT8 sounds like. So what you're hearing are basically 14-second intervals of multiple stations. So, well, I'm going to give me a second here. Let me just get this up on the screen so you can see it a little bit better. So, yeah, let me grab this. Of course. Okay, so hopefully soon enough we'll see some. There we go. So on the right-hand side, these are the various stations that are talking to each other. The ones that are highlighted in green are basically a station indicating that they'd like to make a contact with somebody. So that's their call sign, W0, WO3T, and they're located in what they call a Maidenhead grid square, FN00. Some of these other lines here that don't have the green are basically stations that are establishing a contact with each other through those tones. So if you look at this spectrum down here, which is somewhat represented with this spectrum right here, each one of these little lumps here are really individual contacts. So just within an audio portion of the spectrum, like 2500 hertz, we might have 20 or 30 different contacts going on at the same time. Now the software that Dr. Frissell was talking about is that we use for the meteor scatter is that same suite of software that runs this this equipment here. So like, I'm just sort of looking here at some of these. So F4 JRC, that's a station in France. Let's see, DL5 DQZ, that's a station in Germany. VE2 QWX is up in Quebec. And the other thing that's particularly useful for Dr. Frissell's work is this number right here indicates the signal strength. It's a relative signal strength. So this station right here has a signal strength of 5, very strong. Negative 23 is pretty weak, but yet we're still picking it up. And you can sort of see down in the spectrum down below, the really deep red, that's a nice strong signal. When you get something that's really, really thin, those are those weaker signals. And up here on the map, you can just sort of see these are just little bubbles of locations of where all of those signals are located. And these little squares here, these are what I call the Maidenhead grid square. So here at Kopernik, we're in Maidenhead grid square FN 12. Yeah. You go to Binghamton, we're in Maidenhead grid square 22. Yeah. Anyway, after a while, that gets rather annoying to listen to. But this is extraordinarily powerful software. It was actually co-written by a Nobel Prize-winning physicist, Joe Taylor, K1JT, and it's as I said, the band can appear to be dead because normally, actually, let me go ahead and I'm going to turn off of. Give me a second here, mode. So here's some ham radios doing Morse code, right? And is it going to let me do it? No, it's not. All right. This is a fairly new rig for me, so I'm trying to get it to move off of that particular frequency, and it's not working. But I'm sorry. Yeah, I'm trying to move up into the into the lower sideband section. I'm on the. Oh. There we go. So we're going to go up into the area where you can start hearing. Yep. Okay, so we. Well, anyway, you get a sense of, so that's an active band right now. So if I go to another band, say if I go to 10 meters, see band, where's the band? Oh, right here. I go to 10 meters, and I'm going to go into where we should be able to potentially hear some. Yeah. This is an area where I should be hearing some voice signals, and there's really not much going on. There's maybe one signal here I see. The FT8. Yep. Let's try it again. There's something in there. Yeah, you can sort of hear that. So the people are still even when the band would otherwise is not really very active, you can still make some contacts. So, but any other questions? All right. Well, anyway, I haven't looked outside recently, but we have a rule here, especially for the newcomers, that if you haven't looked through a telescope, you can't leave Kopernik. So, but hopefully there will be some clouds thinning. There's actually an ISS pass at about 10:30, but you don't have to stay for that if you don't wish. But anyway, Dr. Frissell, thank you very much for coming up and talking to us about the work that you and your colleagues do. And we're looking forward to helping it out. As Dr. Frissell had mentioned, the Binghamton Amateur Radio Association does meet here third Wednesday of every month, And we actually run testing sessions. So when you're ready to take your take an exam, you can come and do that here. We're a pretty active club, and so actually at the end of June there's a big event called Field Day, and invite you to come. Even if you don't have your license yet, come on up and check it out. It's a lot of fun, a lot of good people, good friends. It's an active club, and love it to grow even further. So thanks again. Next week we are going to be doing just a casual night of observing. So if it's clear, we invite you to come up for that. Then the following week we have a talk by one of our educators, the history of Planet X. So there's a planet out there, or we think there's a planet out there that seems to be affecting the orbits of all the other planets in our solar system, but we just haven't found it yet. So Olaf Seegers is going to talk a little bit about that. So thanks again for coming, and hope to see you soon.